where we go to create a model. We use all these basically all these different steps or modules that you can also find here. And the first one is to create a part, like for example the velocity. And so here we're going to do a 3D part of this dog-bone tensile experiment. We could do a 2D, but just for the sake of application, we do a 3D part. So it's going to be deformable, and we're going to do it by extrusion, by just drawing this and then extruding it. Remember, in Abaqus there is no unit. You have to use your own set of units. And so here, let's say we're going to use millimeters for length, and then you have to be aware that we'll get stresses in megapascals. You have to use consistent units. You know what I mean. So here we have to draw the sample. So the approximate size basically is just to adapt the grid size here to the length. Yeah. So for example, if I mess up with this, and actually I have a much bigger part, the grid size will not be adapted, and the part will be like this. But it's just for visualization purposes. And so here I'm actually going to load the image. So it's here in the sketcher options, and I can go to image, and I can load an image here by doing create, in the file. I can find here for me. So it should be one of these. It's not too long, I'm going to remove it. Okay. Then we need to calibrate the scale of this image so that we can draw on it. So we can do calibrate. And so here. I have to apply, so it's like it shows. Then you do calibrate. And for example, I'm going to calibrate it on this length here. I'm going to click this point here, and this point here. And it asks for the distance. In my case, it's 165 millimeters. Okay. And now it's calibrated so that the length on this image corresponds to the length in the unit system in Abaqus. I can pick an origin if I want, for example here. Just optional. And then, okay. So, do you have any issues with that? Or is that okay? So when you select the image, so here you click on calibrate, and then it will. So first you have to apply so that it shows. Yeah. Okay. And then when you click on calibrate, you want to click on 2 points on some length that you know basically the length of. So you click on first point, for example, here, and second point, for example, there. And then here it asks for the length. And so you type 165. And now we want to draw on this. So now it's the easy part when you import the image. And so you can use, for example, lines like this. So draw the straight part. example, it will actually be easier to just type the dimensions and draw without drawing on the schematic, but this is quite useful when you have a very complex part and you want to draw something that is not very straight. So let's continue. So here I draw with only straight segments, but of course you can add smoother curves if you like, with splines, something like that. And once you have the full part drawn, so you hit escape and then done. And then it asks for the depth, and in this case, it's 2 millimeters. Okay, and then you have part. So we're going to do one more step. So remember last time, when we want to apply boundary conditions to a specific part of the problem, we have to have some kind of partition. So what I mean is, here we have an example. And we want to simulate a tensile test. And so in the tensile test, basically, these parts are in the tent. And so we need to be able to apply boundary conditions to this part. And so to be able to do this, we need to draw this partition so that we can select this area and we can select this part. So that's what we're going to do now. We're going to do this partitioning. And so to do that, what we want to do is to draw a partition here, for example. So remember, here you have the different tools that can be used to do the partitioning. So it's this icon here. So you can either define a cutting plane, use some already existing plane, extend the existing plane, so different options. So here, I guess, we're going to define the plane first, and then we're going to use this plane to do the partition. And to define a plane, it's this icon here. You can either do an offset from one of the principal planes that is existing, or do an offset from one of the plane of the part. So that's what we're going to do. We're going to do so this is here. This is the second option. So I want to select this plane here on top, and I want to do an offset, either by a value or a point. So here, let's enter a value. I'll click the arrow. Okay. And regarding the dimensions, so let's see. The dimensions here was so 20 like this. Let's see. Okay, maybe a little bit more. So a little bit more. Here you have all the features that you did. And so if I double click on this, I'm able to modify this actually. So here I put 30. Yeah. On a l'impression qu'il y a quelques icônes derrière toutes celles qui ont cette marque là. Donc solution. So 30 seems to be a good offset. Okay. So this, select this, then click on display here, and then enter value and 30. Okay, so we can do it. We can do the same for the plane on the other side. So I do this, enter value. I just need to be aware that I need to flip this arrow so that it goes the other way. Okay. Is that okay for this plane? So now I want to partition the part so that I will be able to apply boundary conditions to the field. So I use this, but clicking again, use that in plane. So it's the second one when you click on it. Long. Okay. And so I select the first one, create partition. Okay. Then I want to partition this cell using this place. Okay. Now I have these two partitions. So let me know if this is okay for you or some problem. size seems appropriate. Even if you want to get more accurate results, you probably want maybe at least 2 or 3 elements in the thickness. So let's okay. Then let's check the element. Well, first let's see how it works. With the mesh. Okay, this is not too bad. Quite good. Remember to mesh the part first. You need to do the seed part and then mesh part. And so let's check the element type. Okay, so on all the regions. So here by default, you see it's a usual 3D stress. So 3D stress is just a 3D library for structural analysis. So maybe we come back to these options if we need to, but at the moment we don't need to change any of those. Remember last time we talked briefly about hybrid formulation when you have almost incompressible materials. That helps with calculating the pressure field. So this should be ticked if we have almost incompressible material. And here you have reduced integration. I didn't talk about this last time. So in classical finite elements, you have a certain number of integration points for each element that allows you to probe for different values and to integrate the fields over the element. And basically, like a standard finite element, you have this certain number of integration points, and Abaqus has this option of reduced integration, where it can evaluate the fields only with one integration point. And so it helps a lot with the speed of the calculation, but it can lead to something that is called Hough-glassing. So if you use Abaqus a little bit, you know what I'm talking about. It's something that happens, for example, when you have a regular element like this, and you have only one integration point. Actually, this configuration, if you have only one integration point, is the same as this configuration. So you have these modes of the formation that do not change the integrated value. And this does not happen when you have general integration. And so in order to control this Hough-glassing, Abaqus has some, I don't know, some black box type of stabilization that is basically Hough-glass control. And use default is probably the best, but if you see these kind of things happening, so specifically at large frame, it can happen. So what happens is that you get things that get a bit deformed like this, and all the mesh actually have this kind of shape that appears. Actually, you know what I'm talking about when you see it. And you will start covering either untick reduced integration or try to use the enhance, and that's what it does. It's enhanced, so it should be better. And then it can help you. So at the moment we use the elements. So now that we have the part, remember we need to assign some materials to it. So here, let's say we do a tensile test on some kind of elastomer. So we use a hyperelastic formulation because it will deform quite a lot. So we create a material that we call elastomer, for example, and we'll assign some hyperelasticity to it. So in mechanical elasticity, hyperelastic. So here we're going to use an isotropic formulation, and we're going to use, let's say, the Ogden strain energy function. So now let's talk a little bit about, then you can click on whatever item you want to get help on. For example, this, and you can show the help. And here it says browsing and modifying material behavior. But the issue is that this is more a contextual help that will help you to know how to fill all these values, but it doesn't say anything about what is an Ogden strain energy function, for example. So for this, let's take a little bit of time to look at the help in Abaqus. So you can open it like this, or you can open it by doing help getting started, for example. And you have this help. And so if you collapse everything, and so you take the help of Abaqus, you see that you have all these categories. And the most notable ones are Abaqus CAE, where it will guide you on how to use these graphical tools, but it will not guide you on what's behind it, basically. In analysis, it will help you understand basically what are the algorithms to reach a solution. So, for example, let's say here we do a static stress displacement analysis. So basically, it tells you what is the solver, how to do a linear analysis, and so on. Then in benchmarks, you have all these problems that can be used to benchmark some kind of, for example, to compare to other code, something like that. For example, I pick one. Let's pick one. Analysis of the state. So there is a definition of the problem with the material properties. All the input files. So we see that what it is, it's different from the CAE files that you get when you use the CAE. And then you have some results. And the same for, so you have all these problems. So for example, let's say you want to model something a bit specific. What you can do is try to look in the benchmarks if you have if there is a problem close to the one you want to use, so that you can start from this and then see how basically the Abaqus guys models your problem and try to see what kind of model they use, what kind of material modeling they use, or if there is some specific options that they use. It's especially interesting when you start on some specific modules, like for example contact mechanics, or let's say damage mechanics, where it can be quite complex, and starting from one of these examples can be a good idea. So in constraints, you have all the help about how to define the constraints in Abaqus, which in the CAE is actually this item here. Then you have definition about all the element types. For example, for us, we were using, let's go back here in the mesh, the type of element can be seen here. C3D8R, which is in common language, 8-node visual element, reduced integration. And so if I want to get help on this type of element, you can go to elements. So it's a continuum element, three-dimensional, and element type. Yeah, you have it here. C3D8R. Somewhere. C3D8 here. And you have basically all the help for this some example problems that are a bit like benchmarks, but sometimes a bit more complex than benchmarks. In benchmarks, usually it's just a specific, very specific model using only one feature. In example problems, you have basically examples using different features together. So, for example, you have, I don't know, indentation of an elastomeric form, for example. Where you have at the same time you have contacts, nonlinear material, and things like this. And once again, it can be helpful to look at these example problems to see whether there's something that could be similar to what you want to do. What else can be interesting? So in our case, for example, remember, I wanted to see what was the Ogden standard function. So it's going to be materials, elastic mechanical properties, hyperelasticity, hyperelastic behavior. So I do that because I know the help quite well, but you can use the search here if you want to look for something. Knowing that this search is not perfect, sometimes it's actually easier to use Google. That will then look up for the actual help page in Abaqus for you. So that's the idea, you can use this search. Yeah. So here I want to look at hyperelastic materials, and here I have strain energy potentials. And for example, let's look at the Ogden form. So the Ogden form is described here, and basically what you have is that you have the principal stretches with some power law, and you have some factor in front of it. So basically it's a very nonlinear behavior with basically the mu parameters. So that's the material. So the mu parameter basically will be the initial stiffness, and the alpha will be the stiffening effect, and d1 will be the compressibility behavior. So note that by default, you can toggle between these two input sources, test data or coefficients. Coefficients is when you already know the parameters of the model, but you might not know the parameters of the model, so you can go to test data, where you can have, for example, tensile experiments that give you stress strain curves, something like that. And so here you see in test data, you can add different kinds of test data, be it uniaxial test data, biaxial, planar, or volumetric. And for example, if I click on one of those, it will ask you for the table of stress strain. For example, if you have a tensile test with stress and strain values, you can fill those in there, and then it will then fit an Ogden model to accommodate for the curves that you showed here, that you put here. So this is quite useful if you have a material but you don't know what kind of constitutive model you will put, is that you can put some values here. So let's put some values just for the sake of so 5, 10, and maybe let's put some values here. So here I have some uniaxial test data now, and what I can do when I click OK is that I can do evaluate here, and in evaluate you see that you should be able to fit different strain energy potentials to your stress strain curve. So it can help when you don't know exactly what strain energy function you want to use. So you can try to fit different strain energy potentials to stress strain curve, and try to see which one fits best. So in this case, let's say that we already have the coefficients. So let's remove this 1.7 megapascal for mu. I took that from a Phonomish customer. 9 for alpha and 1 for G1. Nice specific values. Now we need to remember to a section to assign the material to the element type. So here we're going to do a solid section with homogeneous material using the material that we just created. Okay, and then we need to assign this section to the part. So if we go to part, section assignment, then we will choose all the parts. And we use this section. Okay, so okay. So here we don't need any kind of orientation because we use an isotropic material. So we can go straight to the next step. So this define basically the static calculation step. So we're going to do a static analysis. Here we have just a simple tensor test, no dynamic effects. So we use static analysis with implicit time integration. So here, because it's an elastomer, we're still going to pull quite a lot on it. So we're going to have nonlinear effects due to the material. And also large strains, so we're going to activate nonlinear geometry. Remember, by activating this, you tell Abaqus to recalculate the stiffness matrix to basically do equilibrium recalculation of recalculate the stiffness matrix until the equilibrium is reached. And so this will lead to more time steps, but it's necessary when you have nonlinear effects. For implementation, maybe we can, like last time, if we want intermediate steps, we can tell Abaqus to not go above 0.1 for initial and maximum increment size. So this way we force Abaqus to do at least 10 subsets, and then we will have some results for this thing. Okay. What I missed assembly. In assembly, you need to put your parts. So just double click on instance. Okay. So now we want to apply the boundary conditions that will help us pull on the sample. we're going to do what we did last time. Remember, we're going to couple these regions to a reference point and then apply the boundary condition to this reference point. So first, we're going to do the coupling. So we're going to go to constraints and coupling. So I want to create a reference point that I will use for coupling. So for this, I do choose reference point, and then I select one point somewhere. I can choose any point. I can even put the coordinates here. It doesn't really matter. Take this point, and then so I select it. Okay, and then I will constrain all the surfaces that are here, or basically the top and bottom surface, maybe that's closer to what can be achieved in F, saying that this face and this face are in the clamps. Okay, and then I couple all the degrees of freedom. Now you see that all the degrees of freedom of this face and this face are coupled to this point, and I'm going to do the same for this here. Once again, constraint, coupling. I create a reference point here, okay, and then I select it. I choose the face, this one and this one. Okay, I constrain all the degrees of freedom, and that's it. So now I have constrained all the degrees of freedom of this part to this, and this part to this one. So now what I can do is apply the boundary conditions to these points instead of applying the boundary conditions to all the nodes. And to do that, so what I want to do is to, for example, constrain the displacement of this part and apply some displacement to this part. So I use boundary conditions. I'm going to do, I'm going to use this point, and I'm going to do contrast, so that basically this point will be will not move, and consequently, because it's coupled to all these points, all these nodes from this face, all the points for all this face will not move, which is what happens in the clamps. Then I'm going to do another boundary condition, but this time displacement for this point. And in this case, what I'm going to do is I'm going to keep all of them 0 except some value along x. So I'm going to put 30. So I'm going to try to perhaps deform it by 100%, something like this. And so the initial dimension of this was 57 millimeters. So let's try 50. And so I put minus 50 so that goes in this direction. Okay. And so now everything should be set. So I create a job. Okay. And then I can check whether I have everything. So for this, I can do submit. And it will tell me if there is a problem with the job or not. So here I go a bit faster because I want also to see different options for the post-processing and IMP file. But when you have, I send you the video and you can do all these steps at your own page. So let's look at the monitor. So here, yeah, you see it's completed. Let's look at the warnings because there are some warnings. sometimes these are just warnings, but not necessarily bad. Especially in this case, it's also warning about the copying, saying that, well, basically it was this warning because the tree elements don't have any rotational degrees of freedom. And we couple the rotational degrees of freedom, but yeah, it doesn't matter in this case. So now let's look at the results. And here we see that it deformed quite a lot. So remember last time when we had only very small strain, we had this deformation scale factor that was very high to show that it deformed. Here the deformation scale factor is 1, so the deformation that you see is the real one. We can use this frame selector if you want to browse between the states in the different frames. So what is shown here by default is the von Mises stress, but you can select what output you want here. So here, for example, is deformation frame, so the logarithmic frame. Okay, we see that the last step, the maximum, is about 40%. And we see also that it's quite homogeneous in this area, which is good for something like that. So just so that we can do that once again, using the coupling points, we can extract the total reaction force. So to extract values in Abaqus, we use this, create XY data. We can extract values so here we want something in the field output, and we want something at a nodal, not that utility point, and we want reaction force in direction, I think it's X, direction 1, and we want to select different elements that are in node sets, and that is, for example, the reference points here. So let's plot this, and here you see, as a function of simulation time, you see the reaction force that increases, and you see that it's not linear, which is expected due to the material definition. So here is the total reaction force for the whole specimen. So yeah, we can stop here maybe at the moment. What now? I would like to look at this INP file. So here you see what it says when you start a job. So the job 1 has been created. The job input file job.1.inp has been submitted. And so if you try to look for this job1.inp, so to look for it, you can look for that here, where is Abaqus working at the moment. For that, you can go to set work directory, and it says at the moment it's working in C10. So let's go there and let's check the files. So here you have many files in there that result from previous calculations. But if you go to job 1, you see that you have all these files for job 1. So many of them don't have any extension. I don't like this. I like to have all the extensions always, all my files. Okay. So yeah, now I have all the extensions. So you have different types of files that are created when you do a job. The most important ones are .inp. That is just a text file. You can open for example. And in this file, actually, it's the file that the solver will see. The solver does not interact with the graphical interface, it interacts with this file. Meaning that if you want to write this file by hand and submit it to the solver, it will work. So in these files, actually, it also reproduces basically all these different items items that are in the model, so the parts, the material, the sections, the steps, the interactions, the boundary conditions, except in INT format. So here, for example, you have the part that is defined here with the nodes. So you have node number and then the coordinates. So it goes for all the nodes in the file. Okay. Then you have the elements with the element type here and the connectivity. So this is element number 1 is connected to node 74, 80, 285, and so on. So it's just the connectivity table of the different elements. And you have that for all the elements. Then you have different internal sets that are created that we didn't use but have been created by Abaqus. You have the section here that is defined with the material. And then you have the assembly, where in the assembly, basically you have this instance that comes from this part. We have the 2 nodes, the reference points that we have created. Here you have some internal sets that have been created, the surfaces that we use to do the constraint. And here we have the 2 constraints. So coupling constraints with this reference node and this reference surface, and coupling constraint number 2. Then you have the materials, hyperelastic, Ogden. And then you have the steps. So the step 1 with nonlinear geometry that has been activated. It's a static step. So you might wonder, what do these different options correspond to? And once again, the help can help us. So in the help, you have a section called keywords. And these keywords are basically everything that can be put in the INT file. So for example, here we had the keyword, let's look for the keyword static. Here, okay. And here you have basically all the parameters that you can put to static. And here you have the data line. So the first line shows in first position the initial time increment, 0.1, the time period, 1, the minimum time increment allowed, 1 to -5, and the maximum time increment allowed, 0.1. And this is the same for other sections. For example, boundary. If you look at boundary, you can see how you can define it. You can put some sub-options like amplitude, if you want to define amplitude or something like that. And then data lines, so node number or node set. So here you have the node set 4. No, it's not like this because here you have only two labels. And here we have more than one, so maybe so here, by clicking it shows, that's the one. So node or node sets, first degree of freedom, last degree of freedom, and then the value. So for example here, first degree, so degree of freedom 1 is -50, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0. Then some output requests. So usually when you don't have anything specifically written, it's just that it's the default values. And for default values, once again, you have to use the documentation to know exactly what to use. So you might wonder what is the purpose or the use of this INT file. Actually, like this, it seems much simpler to use the CIE to build the model and to never look at this horrible file and don't understand anything about it. But actually, let's say, for example, you have some script where you want want to do, I don't know, to start a lot of simulations with one varying parameter. So let's say you write a Python or MATLAB script that take an INT file like this and just modify one line. For example, let's just modify this value and then write it as a new INT file and start simulation using this file. So this is much easier using the INT file than the CAE. You can interact with the CAE using scripting, so that you see just after how to do it. But if you just want to modify one set of parameters, it's much more easier to modify it in the INT file directly, because it's just modifying one value in the text file and then submitting the job. So if you want to submit your job from INT file directly, you can do that from the command line. So first you have to navigate to the place where you have this INT file. And then you can submit it by doing Abaqus job equal job 1. And then you can put different options. One option that can be helpful is interactive, so that it shows the progress. And then, so here you already have some result files, so yes, I want to write them. And then here it's only the solver part that takes the INT file, runs the simulation, and completes. And so this way you can automate some, if you want to start multiple jobs, you can automate it within this command. What else? In the INT file also you can include other INT files. For example, let's say I have very, very complex simulation with millions of nodes and different parts and so on. To make this a bit cleaner, I can have, for example, part 1 include such file, and in this file you have the nodes and the elements of the first part. Then include second file where you have the node and elements of the second file, and so on. So you can help making things a bit clearer. And finally, there are some options in Abaqus that can only be used in the INT file, and the option is not here in the CAE. So I don't have any specific example in mind. I think, for example, an isotropic hyperelasticity, I think you don't have everything in the. So yeah, I don't have any specific example in mind, but you might come across some options that can only be used in the INT file, and where there are no way to put them through the CAE. And also, the Abaqus documentation actually is more suited to interacting with the INT file. So for example, if I go to material, look again at this hyperelastic material. And you see here, it shows, for example, how to here in the documentation, most of the documentation deals with the INT files. For example, here you see input file usage. So to put these parameters, you have to use this keyword, and only after it tells you how to do that in the Abaqus CAE. And so you see that most of the time you can do exactly the same thing by either using some Abaqus CAE function or directly writing in the input file. So this can be helpful for scripting, but another thing that can be helpful for scripting is, let's say, for example, example, this time, I want to change one of the dimensions of the part and put that as a parameter and then start multiple simulations. But this time not changing a value in the MP file, but more changing the shape of the part. So to do that, you can either write a script that will automatically remesh using your own mesher or something, and then change all of this, change all the nodes and the connectivity table, and update this. But then you also need to update the node sets, the element sets, and so on, so that it corresponds to the new nodes and element numbers. What would be more useful is that what you can do with Python scripting. So here you see that you have some kind of console view here in Abaqus, and using this you can interact with everything actually, with everything that is in the CE, meaning that every time you click, there is a command that can do the same thing. And actually, one very useful tool to do that is, for example, to perform a command in the CE. Let's see, for example, if I add a new boundary condition to this, for example, and now I want to know how to do this by scripting. So I look for the file that is called abaqus.rpy. I just check that it's this one that is currently used, so it looks like this one, because it's one modified just right now. So I open it. Here you see a lot of things. If you go to the end, you see this command, or this set of commands here, that look like something that has been, for example, used to define the displacement boundary condition. And actually, every time you click, this file updates with a new command that corresponds to a scripting command that has been used to perform the step. And actually, if I take this file and this file only, and I run it as a script, it will recreate all the models and all the steps that I did in the CIE since the start of this session. So I don't know, let's take some here. Here you see, for example, that it looks like it was used to draw some lines. Here, actually, some of these lines, some of these commands sometimes can be, you don't know exactly what they correspond to, but some of them can be are really clear to what they correspond to. So sometimes, there's a bit of trial and error too. So what you can do is take some command from here, then directly run it here, and see what it does. And so this way you should be able to see. So for example, here I have this command. Let's take it. So it should not work. Yeah, it works. Okay. So see, it just changed the view. Okay, because at some point I rotated my viewport, and see here it's just used to change the view. And you can take other set of commands and run them and see what it is. And then you can build a script, maybe by taking this and modifying some values that you can make parametric. And then it will recreate a model, but then maybe you just want, I don't know, some dimension here. At some point when you draw the sketch, you want this dimension to change. And then you can run this file, this script, so it's only the dimension changing. And so it will build the entire model, but only with the dimension different. And this is quite useful when you want to, as I said, to build models where the geometry changes. One thing that you need to be aware of when you write the script is that Abaqus requires, so it's, as you say, but it's Python. So Abaqus requires some imports at the beginning that are those. And so if you want to write your own script, you should always copy this part and put it at the beginning in a new file. Because otherwise some of the options will not be recognized because you will import the right library. No, so you have the option to write in copy paste. You can use tool for debugging, but then you can do a file run script directly, or you can even do that by command line. I don't know the exact command, but you can find it in the documentation. It's something like Abaqus script equal the file. You can start the CE and run the script. And really in the script, you can do anything. You can build a model, you can start a job, you can open the post-processing, you can extract some values. And so this is also very useful, not only when you want to build some parts, but when you want to do automated processing. Let's say that you have this parametric study, where actually in the end, you always extract the reaction force. And so here, you don't want to go to thousands of models, open them, and do X-ray data extraction and so on. So you can write a Python script that does all these steps, and then basically you can start the simulation and then start the Python script to automatically grab all displacement terms. And this is quite useful. And actually, it's very powerful, and the fact that, of course, I can go back again to the documentation. So in documentation, you have something that's called scripting, where here you have some help about we started for scripting. You have some examples, for example, example script here. Let's say creating a new load, getting a stress range. So you have some examples here that also can help you getting started. See, when the script does a very specific task, it's not that long. It's not like a 1,000-line script that we saw before. So here, for example, this script just take the max and min of the stress from a results file. Forgot to tell you in all these files. So the result file is called OGB. That's the one where you have all the simulation results. So if you want to store the result files, you just have to keep this file. When I do my simulations, if I can keep these two files, it means that I can run again the model. I can see all the parameters that were in it, and I have the results as well. So these two files are enough so that you can know everything about the simulation. So here you have some examples of some scripts, and then you also have in scripting reference. You have, by the way, I never use it, but I know you can also interact with C++ instead of Python. You have all the functions that are defined here. So I will use command, for example, or mesh command, assign stack direction, delete mesh. So every function corresponds to something that can be done in C++. And so, yeah, the usual case is using this to automate post-processing. I think it's the most common use of scripting. And now maybe a final thing. So in Abaqus, you have some, for example, you have a library of different constitutive materials, but you can also add your own materials if you like. And the same for, let's say, for example, amplitudes. You have linear amplitudes for increasing the code your own amplitude. Let's say it's very complex, or it depends on one of the output of the simulation. I had this case once where you want the amplitude of the load to depend on one of the fields in the model that is calculated during the solving of the problem. Then you can define your amplitude, and all of this is in user subroutine. And user subroutines are different depending on whether you use the implicit standard solver or the explicit solver. And here you have all the subroutines that you can define. So I talked about amplitude. So you amp, for example. So user subroutine allows you to define the current value of the amplitude, and so on. And here you have the user subroutine that you need to code. So the way you interact is to write a Fortran script. So it's because the Abaqus solver is written in Fortran, so in order to interact with it, you have to write Fortran script. And yeah, it's not the most user-friendly language, Fortran, but it's quite efficient, so that's why it has to be used. The good thing is that in all these subroutines, so one that can be also useful is UMAT, for example, that is a user subroutine for user-defined material. You have all the documentation about how you should define your values, in what reference frame, and so on. So in theory, everything that you need should be in this. In practice, sometimes not that clear. But for example, for user subroutine, you have basically in the user subroutine interface, you have some values that are given as an input, and there are some values that you have to give back as an output in the script. And so here in the head, you have variables to define, and here you have what are the variables, and you have variables that can be updated if necessary, and you have variables passing for information. So typically for a user material, you get the incremental strain, and you want to give back to Abaqus the incremental stress. So it's a typical problem. For amplitude, you want to give back, you have, for example, the time, and you want to give back the actual amplitude, and like that. And then, when you have written this Python script, for which there are some examples, as I said, in each of these subroutines, you need to store it in a file, in a Fortran file, and then when you start the Abaqus job, you just have to say user equal, I don't know, file.f if you have the user subroutine in the file. And one thing that also you need to know is that you need to have a Fortran compiler installed on the computer. So if you really plan to do this, the best bet is either to install a Fortran compiler on your computer, or and I know that I don't think there are free ones, but there are some where you get a few months of trial or something like that. Or you can use the computer cluster at the school where you have the Fortran compiler that is using. But yeah, when you start doing these user subroutines, you can get sometimes not very easy to debug because Fortran is not an easy language first, and there are no hands-on debugging tools that you can use to stop in the middle of the script and see what are the values. So you have to use some print. You have to print some intermediate values, usually in a temporary file or something like that. you have some questions about? Sorry, I really don't have the time to go into details about all this and to give examples about all this. But it was just to give you the possibilities that can exist in Abaqus, and then if you really want to use them, of course you have documentation, but there are also a lot of PhD students, postdocs, or family staff that use these tools, so you can contact me or other people to have some help on all these things. But if you have some questions, go ahead. Let me think about something that can be useful. That can be useful. In the post-processing, when you have many parts, there is a way to hide, show all of these parts. It's using this display group tool, where you, for example, you can hide or show some element sets. You can hide or show some instance. For example, if I remove this, I just remove the visualization. I can add it again. If I want to, I don't know if I have some element sets here. I can remove some part of the problem, see the size, for example. If I go to elements, click from the report, I can remove these elements just visually to see inside. And add them again, and I can create some display groups like this. Check what else can be useful. So yeah, it's using this tool, so create XY data. And so here you have different sub-options. So either you can use history output. So history output is the output of global quantities for the whole simulation, like energy quantities, like external work or something like that. Field output is the different fields that you have. And then one that can be useful also is a path. For example, if you want to extract some values along a specific path. But most of the time, I guess you want some to extract field output for a specific node, for example. And so here, you can either extract values at integration point, at the node, at the face. And depending on what you select, you have different options. For example, at the node, you can extract reaching force, strain, stress, and check, for example, if I want to extract first component of stress for a node. So I click on here, and I can do click from viewport, edit selection, and click on node, and then I can plot stress, and I can save it, which actually shows it here, and here I have it as a values if I want to then copy paste to Excel. And so just maybe one. If you go to result history output, here as I said you have different energy quantities for the model. One thing that can be useful is I talked a little bit about it last time. When you do an explicit simulation and you want to check whether you're at the quasi-static, if you do a quasi-static analysis and you still use the explicit solver, you want your basically you want your kinetic energy to be an order of magnitude lower than the external work that you bring to the system. And so for this, you can plot at the same time kinetic energy and external work. So in our case, it's way that some of the assumptions that you made when creating a model are restricted. The kinetic energy can be compared, for example, with the strain energy. So here in this case, let's check where does the energy go. So you have got external work and strain energy, and they should all be almost perfectly equal because all the external work is going to deform the matter. And finally, if you go to result, field output, or result, I can show you. Result step frame, you can, of course, go to the different steps like this. In result active step frames, you can activate or deactivate some steps if you want so that you can extract results for a specific step. Result section point can be useful, for example, when you have beam elements or shell elements, where you want to extract data at a specific integration point in the thickness. Because by default, be careful, for example, when you have a shell element, by default, the values that you see are at the bottom location. I don't know why. It's at the bottom location of the shell. And so it can be very misleading when you do some bending, for example. Typically, you have a compressive stress and strain at the bottom and tensile at the top. And if you don't select anything, you don't know what's going on. So be aware that you have to. So you can either select bottom, top, envelope, or you can define exactly at what integration points in the thickness you want to result. In field output here, so you can define what field you want, but in options, you can also define in what coordinate system you want to have this result. So by default, so if you don't define any orientation, the coordinate system is the global one. If you define an orientation, the results, typically stress and strain, are expressed in the local coordinate system that you define. And so if you want the results in a specific coordinate system, you can use transformation, user specified, for example, and you build the coordinate system. Or you can even define some coordinate system that move with response or something like this. If you define custom orientation and you want to visualize it, you can plot it in this plot material orientation. So here we don't have it. You have different options, either contours or symbols. For example, you can look at the stress components. Here you can see the stress components, so you get magnitude but also direction of stress using this tool. There are so many options, but I tried to give you the most useful ones. But they're the most useful for me and for you. So, yeah, try to don't hesitate. There are a lot of people using Abaqus actually, so don't hesitate to write those people. So, very good. Thank you.